Forgot to press record, sorry. Okay. Let's okay, so here's an example of a little Excel file I made. So what have I done? So I've done exactly what I've done here, except I've done it on Excel. So here is, I've made a grid of points. So I've made it, that's how fine my grid is, every 0.01. So that's what I've done here. And here I've looked at what sine of kt is. I let k be 1, so this is going to be sine of t at the moment. And this is the derivative. And the way that I did the derivative was, well, since we don't have a formula, I just did rise over run. Okay, so that's, you know that whenever you're stuck on a problem and you don't have a formula to do it, you can always do rise over run. That'll always give you an answer. Okay, so here the blue is sine and the red is the derivative, and it certainly looks pretty cos-like. Okay, so two things. Firstly, it is cosine. Secondly, if you remember your trig, you have to worry about what you measure angles in. Okay, so what are possible ways you can measure angles? What are the two different systems? There's radians, and then what's the other one, more common one? Degrees, right? So degrees is the really old one, goes back to the Babylonians and the Greeks, and radians is the modern invention. When we do it in Excel, the default is radians. And now you can see kind of why, right? Because in radians, the derivative of sine is cosine. If we did it in degrees, that would change k to something like 2 pi on 180, or no, 180. No, 180 divided by 2 pi is the conversion factor. So you would put a k there, and we know that when we multiply by a k, we also multiply the derivative by a k. So this is the reason why we use radians, because it's the same reason why we use e for our base for exponentials. It gives us good derivatives. Using radians gives us good derivatives. Okay, so we can say then that the derivative of sine x is cosine x. Now, what's the effect of multiplying by k? Well, we know what it is by the chain rule, right? Because if we have sine of kx, that's kind of like x goes to u, which is kx, goes to sine u. Derivative of this is k. Derivative of this is cosine u. Multiply them together, and we get that the derivative of sine kx is k times cosine of kx. Let's just illustrate that this is true by doing it on the graph here. So what happens when we change the 1 to a 2? Okay, there's going to be two changes, right? One is that the function moves quicker, right? So that the period is less, the period is halved. But in the derivative, it's also going to multiply the amplitude. So let's just double check that. And there we go. Okay, so again, here's the derivative. Here's the sine. Here's the derivative. Because it's moving quicker, the speed is faster, so the amplitude is doubled. And of course, since I've doubled the inside of it, it halves the period, like we knew before. And if we change that by 0.5, right, it makes it much slower and lower. Okay, to slow things down. Okay, well, what happens if we change sine to cosine? So let's go ahead and do that. So let's change this. I'm going to do cosine now. Here's the derivative of cosine. And I'm going to change the k back to 1. And I've got to change this to cosine here. And I'm going to copy and paste. Okay. So let's see what's going here. So the blue is cosine. Okay, we've seen that before, and we saw that was the derivative of sine. The red is the derivative. Does anyone recognize what the red function is? It's not sine, is it? Because sine would go like that. It's a negative of sine. Yeah. So the derivative of cosine of x is negative sine x. And completing the picture, cosine of kx, well, we know what the chain rule will tell us. We multiply by k. And so let's go and see that in action. Let's do a 3 this time. Okay, moving much faster. So the derivative is now got an amplitude of k of 3, just like we predicted. Okay, so that's pretty straightforward. Okay. So what other things can we do? Let's put that on blank for the time being. What are some other trig functions? Tangent. How can we do the derivative of tangent? Well, does anyone remember a formula for tangent in terms of sine and cosine? Sine over cosine. Quotient. That's why we did it last, because we can do the quotient. Look, we know. So okay. What is it? Low d high. So cosine x. What's the derivative of sine? Cosine. So we get cosine squared minus high derivative of cosine. So we get cosine squared plus sine squared divided by the bottom squared. Does anyone remember what cosine squared plus sine squared is? You've done your trig. It's 1 divided by cosine squared x. So the derivative of tan x is, well, what's 1 over cosine squared? Does anyone remember what 1 over cosine is? Secant, yeah, is secant squared. And in fact, we can figure out all the other trig identities, right? We can figure out cotangent is just is the other one. Secant is 1 over cosine. Cosecant is 1 over sine. So we can figure out the derivatives just by using the trig identity. So really, these are the two ones that you just got to know by heart. You just got to know them cold. Okay, you can figure out all other ones from them. Okay, and so it's just more added to the machine, right? So now you can you really can differentiate any sort of complicated looking thing I can give you. You can break it down and figure out what it is. So let's just do an example of a couple. Let's do e to the x times sine x. Okay, so how's the function put together? It's a product. So you use the product rule. So this is just how you do it. You just figure out, okay, this is that times that. So we just use the product rule. So it's the derivative of e to the x is e to the x times sine x plus e to the x times the derivative of sine x is cosine x. No problem. How about sine of e to the x? How is this function put together? Chain rule, exactly. So it's x going to e to the x going to sine u. So writing down that chain, you know how to do all the parts, just like before. Derivative of this is e to the x. Derivative of this is cosine u. Multiply them together. You get e to the x times cosine of e to the x. What about e to the sine x? Just doing the same thing with different ways. So you can see there's lots and lots of ways you can put things together. How does the chain go this time? Right, so you go x to sine x to e to the u. The derivatives are then cosine x and e to the u. So multiplying them together, you get cosine x times e to the sine x. So you can see just, yeah. Oh, I forgot to do, I should have done e to the x plus sine x, but the derivative of that is just e to the x plus cosine x, right? So there's lots of different ways you can stick things together. But because you know how to differentiate e and how to differentiate sine, you can handle them. Okay. Let's do a couple of examples for you to do. Do cosine of x squared. Okay, so how's this put together? Right, it's a chain. So okay, so now we differentiate the pieces. Derivative of x squared. Derivative of cosine. Negative sine. Okay, replacing the u by. Okay, here's another one. Cosine of 2x divided by x. Have a go at that one. Okay, what's the rule for this one? Okay, so we know then that it's low. What's the derivative of the high? Negative sine 2x. What did you forget? Maybe I didn't 2. Yep, the 2. Minus high d low, which is cosine 2x. Divided by the bottom squared. And just a little bit of tidying up. Minus 2x sine of 2x minus cosine of 2x over x squared. That's a good enough answer. Okay, And last practice one, x times sine x. So quickly do that one. That should be hopefully that should be a breeze for you. Okay, so what rule do we have here? Right rule? Yep. And so it's just x times the derivative of sine, which is cosine, plus the derivative of x, which is 1 times sine x. So that's just x cosine x plus sine x. Okay. So really, you've got all the pieces, all the equipment you need to really differentiate any kind. So if I give you a formula, you should be able to figure out a formula that is its derivative just by applying all the rules. If I give you a table, you can figure out its derivative just by doing little shorter interval as you can. You're trying to put the thing in the midpoint. If I give you a graph, you can figure out the derivative by getting a ruler and drawing a tangent line and bringing out the legs of the triangle and doing rise over run. Okay, so now you know really how to find any derivative. Also, you know what derivatives mean. Okay? It's the rate of change, it's the slope, it's the multiplier, it's the marginal, whatever, so like saying something's got a derivative of 2 means it's increasing. It means that every time you go 1 forward, you go 2 up. So you can figure out all this kind of stuff. You even know about the second derivative. Okay, so the second derivative, you just take the derivative of the derivative, and you know what that means, right? It means concave up or concave down. So we've just finished chapter, whatever it is, 2, I think. Oh no, chapter 3. Okay, so you know what a derivative is and you know how to find it. Okay, so our next step is, well, what can we do with that information? And that's what we go into in chapter 4. But let's just look at a few examples. Okay. Oh, sorry. Should be able to. Okay. Jinru, here is a question. So here's a function. Okay. And here are 4 values that we can get with the function: the amplitude of f, the maximum value, the amplitude, and the maximum value of the derivative. All right. So these are 4 sets of numbers here. Which set of numbers belongs to that function? Hmm? Okay. The answer is E. Okay, let's have a look. Let's go through. The amplitude of F, right, is just 3. Okay, because it's just how much it goes up and down. The maximum value. What is the maximum value? Well, the maximum we can get from this is 3. We add it to 5, we get 8. So 3, 8. Okay. What's the amplitude of the derivative? Right, well, what happens when we take the derivative? We multiply by 2, right? So the amplitude is 6. What's the maximum value? No, because what happens when we differentiate 5? It's 0. So the amplitude, so that is also so the amplitude is also the magnitude. So the actual answer is D. So the answer is D. So you said E, right? Okay. What's the date today? The 11th? Okay. Matt, here's a question from you. So here we've got 4 things, and I want you to put them from smallest to largest in order of the maximum possible values of their slope.
Does it go C, D, A, D?
Hang on, I've got to write this down. So what did you say?
C, D, A, D.
C, D, A, B.
No, C, B, A, D. Other. C, B, A, D.
Oh, C, B, A, D. Sorry.
There you go.
This masks it. Okay, so from smallest to largest. Okay, so when we take the derivative of this, so you're saying this has got the smallest slope? So when we take the derivative,
Oh, yeah, I did that the wrong way.
you went from largest to smallest, didn't you?
Yeah.
I think you did.
Yep.
Yep. Okay, so that was just read the question carefully. So yeah. So this is the steepest because when we pull out the derivative out, we multiply by 3, multiply by 2, multiply by 1, multiply by half, and those are actually going to be because we're going to replace the sine by a cosine, the maximum value of that is 1. So those values are the biggest. Phoebe, are you there? Are you paying attention? Hello? What is it? Oh, okay. Can you turn your sound on and answer the following question? I've never done this before. Or you can answer it by chat if you like. So here we've got this function sine of 4 pi x squared. Okay, so out of those values of x, where does that function attain its largest slope? Does that make sense? So will you think of the same question as well? A half. Okay. Let's try and sort this one out. This isn't that. Sorry, Phoebe. This is a much harder question than anyone else got. Let's give it a try. Okay, so this function is a product, a chain, right? So its derivative is going to be cosine 4 pi x squared, and we're going to be multiplying by the derivative of what's inside, which is 8 pi x. Okay. So at A, the answer is going to be 0, right? Because we're multiplying by this. When x is a half, we've got cosine of pi. What's cosine of pi? Does anyone remember? It's negative, isn't it? So B, the answer is negative. C, cosine of 4 pi is 1. So the answer here, the answer is 8 pi. And at D, again, this is 1, so this is 16 pi. So the answer actually was 2. Thanks, Phoebe. Is Max here?
Yeah.
Hi, Max. Okay, let me try and. So here, I've given you 4 graphs. They're all periodic functions. And so there's sine 2x and sine 3x somewhere in there. So you've got to figure out which is which.
C graph 2 is sine of 2x, or another one. I mean, it should be stretched, right? Like the.
So what is the effect of k when you do sine of kx? So as k gets bigger, what happens to the sine?
Becomes more stretched out.
I don't think so. It becomes quicker, right? Because remember what happens to the derivative. So the derivative of sine of kx is k times cosine of kx, right? So the more that k becomes, the quicker it moves. So the higher the, so sine of 3x moves faster than sine of 2x, which moves faster than sine of x.
Then yeah, it'd be 2x
So
is equal to graph 1, and then 3x is equal to graph 3.
exactly, right? Because all you got to do is recognize that here we have sine of x, right? Because this is 0 to 2 pi. These are the 2 quick ones. This is quicker than that. So that has to be 2x and that is 3x. But yeah, good. Okay, Eric, here's one for you. Which one of these is the graph of sine of x squared? So you just got to try and somehow think of it somehow logically. Let Eric figure it out. B. say. Okay, now what's happening in B? Is it speeding up or slowing down? It's slowing right down. But what's the derivative of sine of x squared? It's 2x times cosine of x squared. So what's happening to 2x times cosine of something? So we've got 2x times a cosine. So is it slowing down or speeding up? It's speeding up, right? Because it's kind of like, it's like the question before that Max answered. 3 was faster than 2, but you've got x squared. So it's kind of like the k is increasing all the time. So we want to look for something where the thing is speeding up. And there's only one of those times which is speeding up, which is, what is that? D. Yeah. So that's it. So even though it looks crazy, just by the fact that you know the derivative, there's only one thing here that it could possibly be, right? And you can eliminate this, right? Because this is just sine x. And this just looks random. What's happening here? So it had to be either this one or this one. This one was slowing down, this one was speeding up. That's how you would have answered the question. Okay. It's still. Let's see. Okay, I've still got more questions for you. Ellie, haven't asked you a question in a while. What about this one? So here we have this function here. How would you start differentiating this?
Well, you use the quotient rule, but what if you have to use the chain rule first? Like technically
Which comes first, the quotient rule or the chain rule?
the quotient rule.
The quotient rule, right? Because first it's a quotient, so then you would. But to do the quotient rule, you have to differentiate the pieces. That's when you use the chain rule. So it's the quotient rule first, and then the chain rule second. Yep. So you use the quotient rule, and then to differentiate the pieces, you'd use the chain rule. Hannah, what about this one here? How would you begin this?
Would it be the quotient? No, it'd be the chain rule.
It'd be the chain rule because this is on the outside. The quotient is inside, so that's going to be done after. So you're going to do the chain rule to do the square root, and then you're going to use the quotient rule to differentiate what's in there. Excellent. Jinru, back to you. What about this one? How would you start doing that? No. What comes before you use the chain rule to do this bit, but what do you have to do before you do the chain rule? So how is it put together? It's put together by a product, right? So you do the product, you'd have to use the product rule first. And then to do this bit, you would use the chain rule. Matt, again, what about this one? How would you begin that one?
Start it. Read the product rule.
Exactly. So the way that it's put together is it's this times this, right? And so then when using the product rule to take the derivatives of these things, you need to do the chain rule. And then while you were doing the chain rule for this, you would have to use the quotient rule. So this one uses all three rules, but you've got to do it in the right order because you've got to see how the thing is put together. So it's always kind of like, you know. Phoebe, you again. Do you see this one? So this one, it's asking, so which of the, how could you differentiate that? Oh, here we go. Chat. Yep, you could use the quotient. Oops, sorry, I lost it. You could use the quotient rule. Yep. Is there another rule you could use? Yep, because so it could be a quotient, right? Because we've got a low divided by a d high, but it's also a chain rule because it's x plus 1 to the power minus 1. So you can use a chain rule from that. Anyone else? Right, because it's like one, you know, so actually this one you can use in any of them that you could do it. So that's just showing you that there's lots of ways sometimes to the same one. Oh, is that an empty? Yes, it's empty. Okay. I'll stop the share there. I think that's good enough. I've tortured you for long enough. Okay, so I'm feeling like people are sort of comfortable with differentiating. Okay, so next we're going to go on to chapter 4, and that's where we're actually going to be using derivatives a lot more. So we've already started doing a little bit of uses, like we've looked at tangent lines and we've looked at approximations and a few economic stuff. We're going to delve deeper into that. Okay, see you Monday. Whew.